Right now, as you watch this video, time is flowing differently across the universe. Near the supermassive black hole at our galaxy's center, 1 second stretches into what would feel like minutes to us here on Earth. Clocks slow down. Hearts beat slower. Thoughts crawl at a cosmic snail's pace. We thought time was universal, the same steady tick everywhere in existence. We were completely wrong. In the most extreme regions near black holes, where gravity becomes so intense it warps the very fabric of reality, time doesn't just slow down, it nearly stops altogether. At the event horizon of a stellar black hole, 1 hour for someone falling in equals 7 years passing in the outside universe. At the edge of a supermassive black hole like Sagittarius A*, the monster lurking at our galaxy's heart, time dilates by factors we can barely comprehend. A day there equals decades here. This isn't science fiction. This is measured, verified reality. NASA's gravitational wave detectors have confirmed it. The Event Horizon Telescope has photographed it. Einstein predicted it over a century ago, and every sophisticated experiment since has proven him right. Time is not the constant metronome we experience in our daily lives. It's elastic, stretchable, and fundamentally tied to the presence of massive objects in ways that challenge everything we thought we knew about existence. Here's what makes this discovery so disturbing. You are living this time dilation right now. Earth's gravity, weak as it seems, is already slowing your clocks compared to empty space. GPS satellites orbiting our planet must account for this effect, or they'd be off by miles within hours. The difference is tiny microseconds per day, but it's real and measurable. Every step you take toward Earth's center, every floor you descend in a building, time moves slightly slower for you relative to someone higher up. The greatest physicists of our time have confirmed these effects with precision that staggers the imagination. Atomic clocks accurate to 1 part in 18 quintillion have measured time dilation caused by height differences of just 1 meter. LIGO detectors stretching 4 kilometers have caught gravitational waves from black hole mergers billions of light years away. Waves that carry the signature of severely dilated time in their cosmic song. The numbers don't lie. Gravity doesn't just pull on matter, it pulls on time itself. What you'll discover tonight will fundamentally alter how you understand your place in this universe. We'll explore how Einstein's stroke of genius revealed time's hidden nature, why massive objects create wells of slow time, and what happens when you approach the point of no return around a black hole. You'll learn about astronauts who age differently than their earthbound colleagues, about atomic clocks that prove your head is aging faster than your feet, and about the mind-bending reality that time travel isn't just possible, it's happening everywhere all the time. But this journey goes deeper than physics formulas and space missions. Tonight, you'll confront a truth that challenges the core of human experience. The time you feel flowing is not fundamental to reality. It's local, personal, and completely dependent on where you happen to exist in the cosmic web of gravity. Near black holes, this truth becomes impossible to ignore. The implications stretch far beyond academic curiosity. Understanding time dilation near black holes reveals how our universe actually works at the deepest level. It explains why nothing can escape from inside a black hole's event horizon, why falling astronauts see the entire future history of the universe flash before their eyes, and why black holes might be the key to understanding the ultimate fate of everything that exists. If you're fascinated by how gravity bends time itself and what this means for our understanding of reality, subscribe and hit the thumbs up button. And here's a mind-bending question. If you could watch someone fall into a black hole, would you see them freeze at the event horizon forever or disappear in seconds? Comment below, I'll pin the most insightful answer. Tonight, we're embarking on a journey to the most extreme environments in the universe, places where the familiar rules of time break down completely. You'll discover that time isn't just relative, it's personal. Every massive object you encounter, from planets to stars to the supermassive monsters at galactic centers, creates its own tempo of existence. Near black holes, this tempo slows to an almost eternal crawl. We'll start with Einstein's revolutionary insight that shattered our understanding of time itself. Then we'll explore exactly how gravity accomplishes this seemingly impossible feat of time manipulation. We'll examine the mathematical relationship between mass, space, and the flow of time, journeying to the event horizon where time dilation reaches its extreme, and finally confront what this all means for your understanding of existence itself. The universe is about to reveal one of its most profound secrets. Time is not what you think it is. And once you understand how black holes stretch seconds into centuries, you'll never look at a ticking clock the same way again. Now let's begin our journey to the places where time itself slows to a crawl. Chapter 1. Relative Time. The revolution that shattered our understanding of time began with a simple observation. Light travels at the same speed no matter how fast you are moving. This seemingly innocent fact would lead Albert Einstein to conclusions so radical they challenged the very foundation of human experience, that time flows at the same rate everywhere in the universe. Before 1905, time was absolute. Newton's clockwork universe ticked along with perfect precision, each second identical whether you measured it on Earth, Mars, or the farthest star. Time was the great constant, the unchanging backdrop against which all motion and change occurred. Physicists believed you could synchronize clocks across the cosmos, and they would remain perfectly matched forever. This intuitive understanding felt obviously correct because it matched our daily experience. But Einstein's special theory of relativity revealed something extraordinary. Time is personal. When you move faster relative to someone else, your clocks literally run slower compared to theirs. This isn't an illusion or measurement error. It's a fundamental property of reality. Time dilation occurs because space and time are woven together into a four-dimensional fabric called spacetime, and motion through space affects your movement through time. To understand this revolutionary concept, imagine two identical atomic clocks, synchronized perfectly. Place one on a high-speed train and keep the other stationary on the platform. As the train accelerates to significant speeds, something remarkable happens. The moving clock begins ticking slower relative to the stationary one. The faster the train moves, the greater this effect becomes. At 90% the speed of light, the moving clock would tick at roughly half the rate of the stationary clock. This time dilation isn't just theoretical. It's been measured with extraordinary precision. In 1971, physicists Haffel and Keating flew atomic clocks around the world on commercial airliners. When they compared these clocks to identical ones left on the ground, they found exactly the time differences Einstein's equations predicted. The flying clocks lost nanoseconds due to their motion through space, proving that high-speed travel literally slows down time. But special relativity only told half the story. Einstein's next insight would prove even more revolutionary. Gravity itself affects the flow of time. In his general theory of relativity, published in 1915, Einstein revealed that massive objects don't just attract other objects, they warp the very fabric of spacetime. This warping creates what we experience as gravity, but it also creates something far more profound: gravitational time dilation. Near massive objects, time runs slower. The stronger the gravitational field, the more dramatically time slows down relative to regions with weaker gravity. This happens because gravity actually curves spacetime itself, and this curvature affects how time flows through that region. You can think of massive objects as creating wells in the fabric of spacetime. The deeper the well, the slower time moves within it. Earth demonstrates this effect constantly, though the changes are incredibly small in our everyday experience. Time runs slightly slower at sea level compared to mountain tops. Your feet age more slowly than your head because they re marginally closer to Earth's center and experience slightly stronger gravity. The difference is tiny, about 90 nanoseconds per year for every meter of height difference, but sophisticated atomic clocks can measure it easily. The practical implications became crucial when humanity began launching satellites. GPS satellites orbit roughly 20,000 kilometers above Earth, where gravity is weaker than at the surface. This means their onboard atomic clocks run faster relative to ground-based clocks, gaining about 38 microseconds per day due to gravitational time dilation. If engineers didn't account for this effect, GPS systems would accumulate errors of several miles within just a few hours of operation. This correction isn't just theoretical housekeeping, it's essential for GPS accuracy. Every time you navigate using your phone, the system is automatically compensating for Einstein dilation effects. The satellites continuously adjust their timing signals based on relativistic calculations, proving that our modern technological infrastructure depends fundamentally on understanding how gravity affects time. The mathematical relationship governing gravitational time dilation reveals its profound nature. The closer you approach a massive object, the more dramatically time slows down. The effect follows a precise formula involving the object's mass, your distance from its center, and the speed of light. For modest gravitational fields like Earth's, the time dilation remains small. But as gravity increases, the effects become increasingly dramatic. Consider what happens as you move closer to the Sun. At Mercury's orbit, time runs about 0.003% slower than on Earth. Barely detectable but real. At the Sun's surface, the time dilation reaches roughly 0.007%. Still small, but beginning to accumulate noticeable differences over extended periods. These measurements have been confirmed through precise observations of light frequencies from the Sun's surface, which appear slightly redshifted due to gravitational time dilation. But the Sun is relatively gentle compared to more exotic objects in our universe. White dwarf stars, the compressed cores left behind after medium-sized stars die, pack roughly the Sun's mass into a volume the size of Earth. Near their surfaces, gravity becomes so intense that time dilation reaches several percent. A clock on a white dwarf surface would run noticeably slower than one in empty space, accumulating minutes of difference over the course of a day. Neutron stars push these effects into truly extreme territory. These cosmic lighthouses compress 1.5 solar masses into spheres only 20 kilometers across, creating gravitational fields so intense they approach the theoretical maximum possible in our universe. On a neutron star surface, time runs roughly 30% slower than in empty space. An astronaut somehow surviving on such a surface would watch the rest of the universe age significantly faster than they do. Yet even neutron stars pale in comparison to black holes. These cosmic monsters represent the ultimate extreme of gravitational time dilation, where Einstein's equations predict that time can slow down by factors of thousands, millions, or even approach complete standstill. Understanding exactly how this happens requires diving deeper into the relationship between gravity, space, and time. As you contemplate these revelations, remember that you are experiencing gravitational time dilation right now. Earth's gravity is continuously affecting your personal flow of time relative to observers in weaker gravitational fields. The effect is minuscule in your daily experience, but it's real and measurable with sufficient precision. Every massive object in the universe creates its own tempo of existence, and black holes create the most extreme tempos of all. The foundation is now established. Time is not universal, not absolute, not constant. It flows differently depending on your motion and your location in gravitational fields. This understanding sets the stage for exploring how black holes take these effects to their ultimate extreme, creating regions where time dilation becomes so severe it challenges our basic understanding of existence itself. Chapter 2. Curved spacetime. To truly understand how black holes slow down time, you must first grasp one of the most profound insights in physics. Massive objects don't just exist in space and time. They reshape the very fabric of both. Einstein's general theory of relativity revealed that what we call gravity is actually the curvature of spacetime itself. And this curvature is what creates the time dilation effects that become extreme near black holes. Imagine spacetime as a vast, flexible membrane stretched tight across the universe. When you place a massive object like a star or planet on this membrane, it creates a depression, a well in the fabric. The more massive the object, the deeper the well. Objects moving nearby naturally follow the curved paths created by these depressions, which we interpret as gravitational attraction. But the curvature affects more than just motion through space. It fundamentally alters the flow of time itself. This isn't merely an analogy. It describes the actual geometry of our universe. Space and time are inextricably linked into a four-dimensional continuum where mass and energy determine the shape of the whole structure. When you change the shape of space-time, you change how time flows through that region. The mathematical description of this relationship, Einstein's field equations, represents one of the greatest intellectual achievements in human history. The key insight is that time and space cannot be separated. They form a unified fabric where motion through one affects your experience of the other. As massive objects curve this fabric, they create regions where time moves at different rates relative to distant observers. The stronger the curvature, the greater the time dilation effect. Black holes represent the extreme end of this spectrum. Objects so massive and compact, they create curvatures so severe that time dilation reaches extraordinary levels. Consider how this curvature develops around different types of massive objects. Our Sun, with its mass of roughly 2 times 10 to the 30th power kilograms, creates a gentle depression in spacetime. Earth orbits within this curved region, following what appears to be a straight line through the four-dimensional geometry, but appears curved to us in our three-dimensional perspective. The time dilation near the Sun remains modest because the curvature, while measurable, is relatively gentle. But imagine compressing the Sun's entire mass into a sphere just a few kilometers across. The same amount of matter, now concentrated into an incredibly small volume, would create a dramatically deeper well in spacetime. This is precisely what happens when massive stars collapse to form black holes. The matter doesn't disappear. It gets compressed to such extreme density that the resulting spacetime curvature becomes almost unimaginably steep. The mathematics of this curvature reveals why black holes affect time so dramatically. Einstein's field equations show that the curvature of spacetime is directly proportional to the energy and matter density within that region. As matter gets compressed into smaller and smaller volumes, the local spacetime curvature increases rapidly. Near the surface of a collapsing star that's becoming a black hole, this curvature grows so extreme that it approaches mathematical infinity. This extreme curvature has profound consequences for time. In regions of severely curved spacetime, the coordinate system itself becomes distorted in ways that stretch time intervals. What appears to be 1 second to someone deep in a gravitational well corresponds to much longer periods as measured by distant observers. The effect is unjust. The clocks run differently. The actual rate at which events unfold becomes fundamentally altered by the local geometry of spacetime. The Schwarzschild solution to Einstein's equations, developed in 1916, provides the mathematical framework for understanding spacetime curvature around spherically symmetric massive objects like black holes. This solution reveals that as you approach the event horizon of a black hole, the curvature becomes so extreme that time dilation approaches infinity. Time doesn't just slow down, it approaches complete standstill relative to distant observers. To visualize this extreme curvature, imagine the space-time membrane stretched to its breaking point. Near a black hole's event horizon, the depression becomes so steep that it's almost like a vertical cliff in the fabric of reality. Objects falling into this region experience increasingly severe time dilation as they approach the point where space-time curvature becomes so extreme that not even light can climb back out of the gravitational well. This curvature explains why nothing can escape from inside a black hole's event horizon. It's not simply that the gravitational pull becomes too strong, it's that the space-time geometry itself becomes so distorted that all possible future paths lead inexorably inward. The curvature literally eliminates any trajectory that could lead back to the outside universe. Even light, following the straightest possible path through this curved space-time, cannot find a route that leads away from the black hole's center. The Event Horizon Telescope has provided stunning visual evidence of this extreme space-time curvature. When the team captured the first image of a black hole in galaxy M87 in 2019, they weren't just photographing an object, they were imaging the effects of severely curved space-time on light itself. The bright ring visible in the image represents photons following curved trajectories around the black hole, with some light rays bent so severely they orbit the black hole multiple times before escaping. But space-time curvature near black holes creates effects beyond simple time dilation. The geometry becomes so distorted that space itself stretches and compresses in different directions. This phenomenon, known as tidal effects, would literally stretch your body if you fell toward a black hole. Your feet, being closer to the black hole's center, would experience stronger gravitational acceleration than your head, creating a stretching force that increases dramatically as you approach the event horizon. The curvature also affects the apparent size and shape of objects near black holes. Light rays following curved space-time paths can create multiple images of the same object. Gravitational lensing effects that bend background starlight around the black hole's immense gravitational field. These distortions provide astronomers with tools for studying black hole properties, but they also demonstrate how profoundly these objects alter the basic geometry of space and time in their vicinity. Recent gravitational wave detections by LIGO and Virgo detectors have revealed another consequence of extreme space-time curvature. When black holes merge, their collision sends ripples through the fabric of space-time itself. These gravitational waves, predicted by Einstein, but only recently detected, represent literal vibrations in the geometry of the universe. The waves carry information about the extreme space-time curvature that exists during black hole mergers, providing direct evidence of how these cosmic monsters warp reality. The mathematical description of space-time curvature near black holes involves tensor calculus and differential geometry advanced mathematics that describes how the fundamental metric of space and time changes from point to point. While the equations are complex, their physical meaning is profound. Mass doesn't just attract other mass. It reshapes the stage on which all physical processes unfold. Near black holes, this reshaping becomes so extreme that time itself becomes almost unrecognizably distorted. As you contemplate these ideas, consider that you are living within curved spacetime right now. Earth mass creates a small but real curvature in the fabric of reality around you. Your experience of falling when you drop an object isn't caused by a mysterious force pulling downward. It is the result of objects following straight lines through curved spacetime. The time dilation you experience due to Earth's gravity is a direct consequence of this curvature, affecting how time flows in your local region of spacetime. Understanding spacetime curvature is essential for grasping how black holes create their extreme time dilation effects. The curvature doesn't just slow down clocks, it fundamentally alters the geometric relationship between space and time. Near black holes, this alteration becomes so severe that the familiar concepts of simultaneity, duration, and temporal sequence break down completely. The stage is set for exploring exactly what happens to time as you approach these cosmic monsters. Chapter 3: Event Horizon, The event horizon represents the ultimate boundary in our universe, the point of no return around the black hole where time dilation reaches its most extreme manifestation. This invisible sphere surrounding every black hole marks the location where spacetime curvature becomes so severe that time, as measured by distant observers, appears to slow to a complete stop. Understanding what happens at this cosmic boundary reveals the most mind-bending aspects of how gravity affects the flow of time. The event horizon isn't a physical surface like the edge of a planet or star. It's a geometric boundary defined purely by the extreme curvature of spacetime itself. The radius of this boundary, called the Schwarzschild radius, depends only on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of roughly 3 kilometers. For the supermassive black hole at our galaxy center, containing 4 million solar masses, the event horizon spans about 24 million kilometers, roughly 17 times the distance from Earth to the Sun. What makes the event horizon so significant for time dilation is that it represents the mathematical limit where gravitational time dilation approaches infinity. As you approach this boundary from the outside, time slows down more and more dramatically relative to distant observers. At the event horizon itself, according to Einstein's equations, time dilation becomes infinite, meaning that events at the horizon appear completely frozen when viewed from a safe distance away. This creates one of the most counterintuitive paradoxes in physics, the frozen star paradox. Imagine watching an astronaut fall toward a black hole. As they approach the event horizon, you would see their descent slow down dramatically. Their watch would appear to tick slower and slower. The light from their flashlight would become redder and dimmer as gravitational effects stretch the wavelengths. Eventually, the astronaut would appear to freeze at the event horizon, suspended there forever from your perspective. But here's what makes this scenario so profound. From the falling astronaut's perspective, nothing unusual happens as they cross the event horizon. Their watch continues ticking normally. They don't experience any slowing of time. They fall through the boundary in a finite amount of time according to their own measurements. The time dilation that appears extreme to distant observers is completely undetectable to someone actually experiencing the fall. This stark difference between perspectives reveals a fundamental truth about time in Einstein's universe. There is no universal now. Events that appear simultaneous to one observer occur at different times for another observer in a different gravitational field. The astronaut crosses the event horizon at a specific moment in their personal timeline, but this moment corresponds to the infinite future in the timeline of distant observers. The mathematics describing time dilation near the event horizon involves what physicists call coordinate time versus proper time. Coordinate time is what distant observers measure, the time that appears on clocks far from the black hole. Proper time is what someone falling into the black hole measures on their own clock. As the falling observer approaches the event horizon, coordinate time stretches toward infinity while proper time continues flowing normally. This extreme time dilation has observational consequences that astronomers have actually detected. When matter falls toward a black hole, it often forms an accretion disk, a swirling, superheated spiral of gas and dust. Material in this disk experiences severe time dilation as it approaches the event horizon. From our distant perspective, we see this material slowing down and becoming redshifted as it nears the point of no return. The Event Horizon Telescope's historic image of the black hole in galaxy M87 captured evidence of this time dilation effect. The bright ring visible in the image represents photons orbiting just outside the event horizon in the photosphere, the region where light can orbit the black hole in unstable circular paths. These photons experience extreme time dilation, and their observed properties confirm Einstein's predictions about spacetime curvature near the event horizon. But the event horizon creates effects beyond simple time dilation. The extreme spacetime curvature at this boundary fundamentally alters causality itself. Inside the event horizon, the roles of space and time coordinates become mathematically exchanged. What we normally think of as the spatial coordinate pointing toward the black hole center becomes time-like, while what we normally consider time becomes space-like. This mathematical transformation means that falling toward the center becomes as inevitable as moving forward in time. Understanding the event horizon also reveals why black holes are truly black. Light emitted from inside the boundary cannot escape because all possible future light paths lead inexorably inward due to the extreme space-time curvature. The horizon marks the boundary where the escape velocity equals the speed of light, but more fundamentally, it marks where space-time geometry eliminates any possible escape trajectory. Recent theoretical work has revealed that the event horizon may have even more exotic properties. Some physicists propose that quantum effects near the horizon create a firewall, a region of intense energy that would incinerate anything attempting to cross. Others suggest that the horizon is a hologram-like surface that encodes information about everything that has ever fallen into the black hole. These ideas remain highly speculative, but they demonstrate how the extreme time dilation near the event horizon connects to some of the deepest unsolved problems in physics. The size of the event horizon scales directly with the black hole's mass, which has important implications for time dilation effects. Stellar mass black holes, formed from collapsed stars, have event horizons only a few kilometers across. The extreme space-time curvature near these compact horizons creates dramatic tidal effects that would tear apart any object long before reaching the boundary. Supermassive black holes, by contrast, can have event horizons larger than planetary orbits, with much gentler tidal forces that would allow objects to cross intact. This size difference affects the time dilation experienced during the approach to the event horizon. Near a stellar mass black hole, the final moments before crossing involve rapid acceleration and extreme tidal stretching. Near a supermassive black hole, the approach is more gradual, with time dilation building up slowly over a much larger region. In both cases, though, the mathematical result is the same: infinite time dilation at the horizon itself. Gravitational wave detections have provided unprecedented insights into what happens when event horizons merge. When two black holes spiral into each other, their individual event horizons eventually touch and merge into a single, larger horizon. The gravitational waves emitted during this process carry information about how space-time curvature evolves during the merger, providing direct observational evidence of event horizon dynamics. The concept of the event horizon also raises profound questions about the nature of information in our universe. If information that falls past the event horizon can never escape, what happens to it? This information paradox remains one of the greatest unsolved problems in theoretical physics, connecting black hole physics to quantum mechanics and thermodynamics in ways that continue to challenge our understanding. For rotating black holes, the situation becomes even more complex. The Kerr solution to Einstein's equations describes how rotation affects spacetime geometry around black holes, creating additional boundaries beyond the simple event horizon. The ergosphere region outside the event horizon, where spacetime itself is dragged around by the black hole's rotation, adds new layers to how time dilation develops near these cosmic monsters. As you consider the event horizon's role in extreme time dilation, remember that this boundary represents the most extreme manifestation of effects that operate throughout the universe. Every massive object creates some degree of time dilation, but black holes push this effect to its mathematical limit. The event horizon is where time dilation becomes infinite, a cosmic boundary where our normal understanding of temporal flow breaks down completely. The journey to understanding time dilation near black holes requires confronting this ultimate boundary where time itself appears to stop. The event horizon represents not just a point of no return for matter and energy, but a fundamental limit to how time can flow in our universe. Beyond this boundary lies a realm where time dilation gives way to even stranger phenomena. Chapter 4. Falling Clocks. When you drop a clock toward a black hole, something extraordinary happens that illuminates the deepest nature of time dilation. The clock doesn't just slow down. It reveals that time itself is fundamentally personal and observer-dependent. This thought experiment, when carried out with mathematical precision, unveils how gravitational time dilation manifests in the most extreme environments and why black holes represent the ultimate test of Einstein's theories about space and time. Imagine releasing an identical atomic clock at various distances from a black hole, while keeping one as a reference at a safe distance. As each clock falls inward, it begins to tick at different rates compared to your reference clock. The closer a falling clock approaches the black hole, the more dramatically its ticking slows down relative to your distant reference. This isn't instrument failure or measurement error. It's the fundamental nature of time in curved spacetime. The mathematical relationship governing this time dilation follows Einstein's general relativity equations with stunning precision. At twice the Schwarzschild radius, a falling clock ticks at about 71% the rate of a distant reference clock. At 1.5 times the Schwarzschild radius, the falling clock slows to roughly 58% of the distant rate. As the falling clock approaches the event horizon, its apparent ticking rate approaches zero from the perspective of distant observers. But here is where the physics becomes truly remarkable. From the perspective of someone traveling with the falling clock, nothing unusual happens to their timepiece at all. Their atomic clock continues ticking at its normal rate. Their heartbeat maintains its regular rhythm. Chemical reactions proceed normally. The time dilation is purely relative. It only becomes apparent when comparing measurements between observers in different gravitational fields. This principle of general covariance, that the laws of physics are the same for all observers regardless of their motion or location, represents one of Einstein's most profound insights. There is no absolute reference frame that can determine which clock is really running slowly. Each observer measures time according to their local conditions, and all measurements are equally valid within their respective reference frames. The practical implications of this relativistic principle become visible in real astronomical observations. When matter spirals into black holes, forming accretion disks, astronomers can actually observe time dilation effects in the emitted radiation. Material closer to the black hole appears to emit light at lower frequencies due to gravitational redshift, a direct consequence of time dilation, affecting the electromagnetic radiation wavelength. NASA's Nuclear Spectroscopic Telescope Array has detected iron emission lines from gas orbiting close to black holes, with the radiation showing precisely the gravitational redshift patterns Einstein's equations predict. These observations provide direct evidence that clocks, whether atomic oscillations or electromagnetic wave cycles, genuinely run slower in the intense gravitational fields near black holes. But falling clocks reveal another subtle aspect of time dilation. The effect builds up gradually, rather than occurring suddenly at any specific boundary. As a clock falls toward a black hole, the time dilation increases smoothly and continuously. There is no magic radius where time suddenly starts behaving differently. The effect strengthens progressively as gravitational field strength increases. Consider the detailed trajectory of an atomic clock dropped from rest at a great distance from a black hole. Initially, the time dilation is negligible. The clock ticks almost normally compared to distant references. As the clock picks up speed in its fall, special relativistic effects, due to its motion, begin to contribute additional time dilation on top of the gravitational effects. The combination of gravitational and kinematic time dilation creates a complex pattern of clock behavior. Near the innermost stable circular orbit, the closest, distance where matter can orbit a black hole without spiraling inward. Time dilation reaches dramatic levels even before the final plunge begins. For a Schwarzschild black hole, this orbit exists at 3 times the Schwarzschild radius, where clocks run at about 50% the rate of distant references. Material orbiting at this distance experiences time flowing at half the rate compared to the outside universe. The detailed mathematics of falling clocks also reveals fascinating coordinate dependencies. The Schwarzschild coordinate system, commonly used to describe black hole spacetime, predicts that falling clocks appear to slow down dramatically and never actually reach the event horizon from the perspective of distant observers. However, alternative coordinate systems like Kruskal-Schiker's coordinates show that falling clocks do cross the event horizon in finite proper time. This coordinate dependence isn't a flaw in the physics. It reflects the profound truth that simultaneity becomes ill-defined in curved spacetime. Events that appear simultaneous to distant observers occur at different times for falling observers, and vice versa. The choice of coordinate system affects how you describe the timing of events, but the physical reality experienced by each observer remains independent of these mathematical conventions. Quantum mechanics adds additional layers of complexity to falling clock behavior near black holes. Quantum field theory in curved spacetime predicts that accelerated observers, including those falling in gravitational fields, detect thermal radiation where inertial observers detect none. This Unruh effect means that falling clocks might register subtle temperature increases due to their acceleration, providing another window into how extreme gravity affects fundamental physics. The information paradox connected to falling clocks raises profound questions about the nature of quantum information. If a clock carrying quantum information falls past a black hole's event horizon, what happens to that information from the perspective of external observers? The clock appears frozen at the horizon forever, suggesting the information becomes inaccessible. But quantum mechanics demands that information cannot be destroyed. Recent theoretical work suggests that falling clocks might experience firewalls at the event horizon regions of intense quantum radiation that would destroy any classical object attempting to cross. This firewall hypothesis attempts to resolve the information paradox, but creates new puzzles about the nature of spacetime near event horizons. The debate continues among theoretical physicists about whether classical falling clocks could actually survive crossing into black holes. Rotating black holes, described by the Kerr metric, create even more complex behavior for falling clocks. The rotation drags spacetime around the black hole, creating regions where clocks must move in the direction of rotation just to maintain constant position relative to distant observers. In the ergosphere, the region outside the event horizon where this frame dragging becomes, extreme falling clocks experience additional time dilation effects due to the rotational energy of the black hole itself. Laboratory tests of gravitational time dilation provide practical verification of these theoretical predictions. The Pound-Rebka experiment in 1959 used the Mach-Bauer effect to measure gravitational redshift in gamma rays traveling just 22.5 meters up a tower at Harvard University. More recent experiments with atomic clocks have detected time dilation differences over height variations of less than a meter, confirming that the same physics governing falling clocks near black holes operates at all scales. GPS satellite systems provide daily practical applications of falling clock physics. The satellites experience both gravitational time dilation due to their distance from Earth and special relativistic effects due to their orbital motion. Engineers must account for both effects to maintain navigation accuracy, demonstrating that time dilation isn't just an exotic phenomenon near black holes. It is a practical consideration for modern technology. As falling clocks approach black holes, they also experience increasing tidal effects that would eventually stretch and compress any physical object. For stellar mass black holes, these tidal forces become lethal long before reaching the event horizon. For supermassive black holes, tidal effects remain manageable until much closer to the horizon, allowing hypothetical falling clocks to survive much deeper into the extreme time dilation regime. The study of falling clocks near black holes continues to drive advances in both theoretical physics and observational astronomy. Future gravitational wave detectors may be sensitive enough to detect the final moments of objects falling into black holes, providing unprecedented data about time dilation in the most extreme gravitational fields. These observations could test general relativity in regimes never before accessible to human investigation. Understanding falling clocks near black holes reveals time dilation as more than just a curious relativistic effect. It is a window into the fundamental structure of reality itself. When gravity becomes strong enough, it doesn't just affect how fast clocks tick, it challenges our basic concepts of simultaneity, causality, and the flow of time. Chapter 5. Gravitational redshift light itself becomes a messenger of time dilation near black holes, carrying in its wavelength the signature of how severely gravity has warped the flow of time. This phenomenon, called gravitational redshift, provides one of the most direct and observable manifestations of time dilation, allowing astronomers to measure the effects of extreme gravity by analyzing the color and frequency of electromagnetic radiation escaping from near black holes. When light climbs out of a gravitational field, it loses energy, not because anything absorbs that energy, but because the time dilation in the gravitational field affects the rate at which electromagnetic oscillations occur. A photon emitted from a region where time runs slowly will appear redshifted when observed from a region where time runs faster. This redshift isn't due to motion like the Doppler effect. It's a direct consequence of gravitational time dilation affecting the fundamental frequency of electromagnetic radiation. The mathematical relationship between gravitational redshift and time dilation follows directly from Einstein's general relativity. If time runs slower by a factor in a gravitational field, then electromagnetic waves oscillating in that field will also have their frequency reduced by the same factor when observed from outside the field. This means that gravitational redshift provides a direct measurement of time dilation. The amount of redshift tells you exactly how much time is slowed down in the emitting region. Near black holes, this gravitational redshift becomes extreme. Light emitted from the innermost stable circular orbit around a black hole, the closest distance where material can maintain a stable orbit, experiences redshift factors that can reach 50% or more. Light that started as blue becomes red. X-ray emission shifts into optical wavelengths. The entire electromagnetic spectrum gets stretched toward longer wavelengths as photons climb out of the deep gravitational well. This redshift provides astronomers with a powerful tool for studying black holes. The Event Horizon Telescope team used gravitational redshift effects to help determine the mass and rotation rate of the supermassive black hole in galaxy M87 by measuring how much the radiation from near the black hole was redshifted compared to expected values. They could calculate the strength of the gravitational field and thereby determine the black hole's properties. Iron emission lines from gas-orbiting black holes provide particularly clear examples of gravitational redshift in action. Iron atoms near black holes emit characteristic X-ray spectral lines at well-known frequencies. When astronomers observe these lines using space telescopes like Chandra or XMM-Newton, they find the lines shifted to lower frequencies in precisely the pattern Einstein's equations predict for extreme gravitational redshift. The European Space Agency's XMM-Newton telescope has detected iron emission lines from gas orbiting just outside the event horizons of several black holes. These observations show redshift factors indicating time dilation of 30 to 50%, meaning that atomic processes in these regions occur at half the rate compared to our reference frame. This represents some of the most extreme time dilation ever directly observed in the universe. But gravitational redshift near black holes reveals subtleties beyond simple time dilation measurements. As light escapes from different regions around a black hole, it experiences varying amounts of redshift depending on the exact trajectory it follows. Light emitted from the side of an accretion disk moving toward us experiences less redshift than light from the receding side, creating asymmetric spectral line profiles that encode information about the orbital motion and gravitational field structure. This complex redshift pattern allows astronomers to map the spacetime geometry around black holes with remarkable precision. By analyzing how spectral lines are stretched and shifted across different parts of the emission region, scientists can test Einstein's predictions about black hole spacetime and search for deviations that might indicate new physics beyond general relativity. Gravitational redshift also demonstrates the equivalence principle in its most extreme manifestation. Einstein realized that gravity and acceleration are fundamentally equivalent, an insight that led directly to general relativity. Near black holes, this equivalence means that the redshift caused by intense gravity is identical to what would be observed from an accelerating reference frame moving away from the source at increasing speeds. The quantum mechanical implications of extreme gravitational redshift near black holes reveal connections to some of the deepest unsolved problems in physics. As photons climb out of increasingly deep gravitational wells, their wavelengths stretch toward infinity as they approach emission from the event horizon. This infinite redshift corresponds to the infinite time dilation at the horizon and raises questions about information preservation and black hole thermodynamics. Hawking radiation, the theoretical thermal emission predicted to arise from quantum effects near black hole event horizons, would exhibit extreme gravitational redshift as it escapes from near the horizon. The redshift would be so severe that even high-energy quantum fluctuations near the horizon would appear as extremely low-energy radiation to distant observers, potentially explaining why Hawking radiation has never been directly detected from astrophysical black holes. Recent advances in astronomical instrumentation have enabled increasingly precise measurements of gravitational redshift from black hole environments. The upcoming James Webb Space Telescope and next generation, extremely large ground-based telescopes will have the sensitivity to detect gravitational redshift from individual stars orbiting close to supermassive black holes, providing new tests of general relativity in the strong field regime. The star S2, which orbits the supermassive black hole at our galaxy's center, provides an excellent laboratory for studying gravitational redshift. During its closest approach in 2018, S2 reached about 120 times the radius of the black hole's event horizon, where gravitational redshift effects become clearly detectable. Observations during this close passage confirmed Einstein's predictions with unprecedented precision. Gravitational redshift measurements also provide insights into black hole rotation. The Kerr metric describing rotating black holes predicts specific patterns of redshift depending on the black hole's angular momentum. Frame dragging effects near rotating black holes create additional Doppler shifts that combine with gravitational redshift in characteristic ways, allowing astronomers to determine both the mass and rotation rate of black holes from spectroscopic observations. The connection between gravitational redshift and time dilation becomes especially clear when considering the emission and absorption of light by atoms in strong gravitational fields. An atom falling toward a black hole experiences normal physics from its own perspective. Its electrons orbit at normal frequencies, and it emits light at characteristic atomic transition frequencies. But from a distant observer's perspective, the atom's internal processes appear slowed down due to time dilation, causing its emission lines to appear redshifted. Laboratory experiments have confirmed the gravitational redshift effect with extraordinary precision, validating the same physics that operates near black holes. The Pound-Rebka experiment used gamma rays traveling in Earth's gravitational field to measure redshift over a height difference of just 22.5 meters. More recent atomic clock experiments have detected fractional frequency changes smaller than 1 part in YP, demonstrating that gravitational redshift operates at all scales. GPS satellites provide a practical example of how gravitational redshift affects modern technology. The satellite clocks run faster than ground-based clocks due to weaker gravitational fields at orbital altitude. This time difference causes the satellite radio signals to be shifted to higher frequencies compared to ground references. GPS receivers must account for this frequency shift to maintain accurate positioning calculations. Gravitational redshift also offers a potential method for detecting primordial black holes, hypothetical, small black holes that might have formed in the early universe. If such objects exist, their extreme gravitational fields would produce distinctive redshift signatures in any radiation they emit or scatter. Future sensitive observations might detect these signatures, providing evidence for exotic black hole populations. The study of gravitational redshift near black holes continues to push the boundaries of observational astronomy and theoretical physics. Next-generation gravitational wave detectors may be sensitive enough to detect frequency changes in gravitational wave signals as they propagate through the curved spacetime near black holes, providing new ways to study gravitational redshift in dynamical, strong-field environments. Understanding gravitational redshift reveals how electromagnetic radiation serves as a direct probe of spacetime curvature and time dilation. Every photon carries information about the gravitational field it has experienced, encoding in its frequency the story of how severely gravity has warped time in the regions through which it has traveled. Near black holes, this story becomes one of extreme time dilation written in the language of stretched and reddened light. Chapter 6. Inside Horizons Crossing. The event horizon of a black hole marks entry into a realm where the familiar relationship between space and time becomes fundamentally altered. Yet the paradoxes of time dilation reach their most profound expression. What happens to time inside a black hole challenges every intuition about temporal flow and reveals aspects of reality that stretch human comprehension to its limits. From the perspective of someone falling across the event horizon, the crossing itself occurs in finite proper time, perhaps just a few milliseconds for a stellar mass black hole or several minutes for a supermassive one. Their watch continues ticking normally. Their biological processes proceed unchanged, and they experience no sudden discontinuity in their personal timeline. The event horizon, despite its cosmic significance, passes by like an invisible boundary marked only by the point of no return. But the space-time geometry inside the horizon reveals something extraordinary. The mathematical roles of space and time coordinates become interchanged compared to the external universe. The radial coordinate pointing toward the singularity becomes time-like, meaning that falling toward the center becomes as inevitable as moving forward in time. The time coordinate becomes space-like, indicating that different times inside the black hole correspond to different spatial regions rather than temporal moments. This coordinate transformation has profound implications for causality inside black holes. All future directed paths lead inexorably toward the central singularity, where space-time curvature approaches mathematical infinity. There are no possible trajectories that could lead away from the center or back toward the event horizon. The interior geometry creates a region where the normal relationship between cause and effect becomes twisted in ways that defy everyday experience. The Penrose diagram, a mathematical tool for visualizing the global structure of black hole. Spacetime reveals the interior as a region where world lines converge toward the singularity in finite proper time. From the perspective of infalling matter, the journey from event horizon to singularity takes only moments, during which the gravitational tidal forces increase exponentially until they become strong enough to overcome any material strength. But here's where time dilation creates its most mind-bending paradox. While someone falling into a black hole experiences a brief journey to the singularity, they also witness something extraordinary happening in the universe outside. Due to the extreme time dilation effects, the falling observer sees the entire future evolution of the external universe compressed into the brief time before reaching the singularity. This effect occurs because light from the outside universe becomes increasingly blue-shifted as observed by the falling observer. While gravitational redshift makes light escaping from the black hole appear redder to outside observers, the reverse effect makes external light appear bluer and more energetic to infalling observers. In the most extreme case, the falling observer might witness the entire future history of the cosmos flash before their eyes in the final moments, before hitting the singularity. The mathematical description of this effect involves analyzing light ray trajectories in Schwarzschild spacetime. Light rays from the external universe that catch up with a falling observer just before the singularity originated from arbitrarily far in the future as measured by external coordinates. This creates a situation where the interior of a black hole becomes a window into the ultimate fate of the surrounding universe. Recent theoretical work has revealed additional complexities about the nature of time inside black holes. Some solutions to Einstein's equations suggest that black hole interiors might contain regions where time appears to flow backward or where closed time-like curves could theoretically exist. These possibilities remain highly speculative and may be eliminated by quantum effects or cosmic censorship principles that prevent such extreme violations of causality. The singularity itself represents the ultimate breakdown of our understanding of spacetime. At this point, density becomes infinite, spacetime curvature diverges, and the mathematical machinery of general relativity fails completely. Whether time has any meaningful definition at the singularity remains an open question that may require a quantum theory of gravity to answer definitively. Rotating black holes, described by the Kerr metric, create even more exotic possibilities for time inside the event horizon. These solutions contain an inner horizon beyond which the spacetime geometry exhibits negative energy densities and potentially unstable behavior. Theoretical analysis suggests that the inner regions of rotating black holes might be destroyed by quantum instabilities, long before classical and falling matter could reach them. The firewall hypothesis proposes that quantum effects near the event horizon create a region of intense energy density that would incinerate anything attempting to cross into the black hole interior. If correct, this would mean that the smooth spacetime geometry predicted by classical general relativity breaks down at the horizon, and the interior might not exist in any recognizable form. The debate over firewalls continues to drive research at the intersection of black hole physics and quantum mechanics. Quantum field theory in curved spacetime predicts additional exotic phenomena inside black holes. Virtual particle pairs created by quantum fluctuations might become real particles in the intense gravitational fields, potentially filling the interior with radiation fields that could affect a local geometry. These quantum corrections to classical general relativity remain poorly understood but might fundamentally alter the nature of black hole interiors. The holographic principle suggests an even more radical possibility that the information describing anything inside a black hole is actually encoded on the two-dimensional surface of the event horizon. If correct, this would mean that the three-dimensional interior is redundant, a holographic projection of information stored on the boundary. This principle challenges the notion that black hole interiors exist as independent regions of spacetime. Recent advances in numerical relativity have enabled computer simulations of black hole formation and merger that provide insights into interior dynamics. These simulations suggest that the approach to the singularity involves complex interactions between gravitational waves, matter fields, and spacetime curvature that create rich dynamics in the final moments before the singularity forms. The connection between black hole interiors and cosmology has led to speculation about whether singularities might serve as bridges to other regions of spacetime or even other universes. Einstein-Rosen bridges, theoretical wormhole connections through black hole interiors, remain mathematically possible in general relativity, but would likely be unstable and non-traversable due to quantum effects and classical instabilities. Information preservation inside black holes presents one of the greatest challenges to our understanding of fundamental physics. If information falling into a black hole is lost when the black hole eventually evaporates through Hawking radiation, this would violate fundamental principles of quantum mechanics. Resolution of this information paradox may require new physics beyond our current theories. The study of black hole interiors also connects to questions about the ultimate fate of information in our universe. As the cosmos expands and cools, most matter may eventually collapse into black holes, and these black holes will slowly evaporate through Hawking radiation. Understanding what happens to information inside black holes during this process may determine whether information has any permanent existence in our universe. Observational tests of black hole interior physics remain challenging because information from inside the event horizon cannot escape to reach external observers. However, gravitational wave signals from black hole mergers provide indirect probes of interior dynamics, and future detections may reveal signatures of exotic physics inside these cosmic monsters. The contemplation of time inside black holes pushes human understanding to its limits and beyond. These regions represent laboratories where general relativity encounters quantum mechanics in the most extreme possible conditions. The resulting physics may ultimately require revolutionary new theories that transcend our current understanding of space, time, and reality itself. As we peer into the cosmic abyss of black hole interiors, we confront the ultimate boundaries of physical law and the deepest mysteries about the nature of existence. The journey inside reveals not just extreme time dilation, but fundamental questions about causality, information, and the basic structure of reality that continue to challenge the greatest minds in physics. Chapter 7. Observable Effects. The extreme time dilation near black holes isn't merely a theoretical curiosity. It produces observable effects that astronomers can detect and measure using sophisticated instruments, providing direct evidence for Einstein's most profound predictions about the nature of space and time. These observations have transformed our understanding from mathematical equations into verified reality, revealing a universe where time truly flows differently near the most massive objects. The most dramatic observable evidence comes from matter spiraling into black holes through accretion disks, vast whirlpools of superheated gas that can outshine entire galaxies. As material orbits closer to the event horizon, it experiences increasingly severe time dilation that affects every aspect of its electromagnetic emission. Astronomers observing these systems see direct evidence of time slowing down in the form of red-shifted spectral lines, stretched oscillation periods, and modified brightness patterns. NASA's Rossi X-ray Timing Explorer detected quasi-periodic oscillations from several black hole systems that show precisely the time dilation effects Einstein predicted. These oscillations represent matter orbiting close to the black hole's innermost stable orbit, where time dilation reaches 50% or more compared to distant observers. The observed frequencies match theoretical calculations based on general relativity with extraordinary precision, providing some of the strongest confirmations of extreme gravitational time dilation. The European Space Agency's X and M Newton telescope has revolutionized observations of time dilation effects by detecting iron emission lines from gas orbiting just outside black hole event horizons. Iron atoms emit X-rays at characteristic frequencies, but when observed from these extreme environments, The lines appear dramatically redshifted due to gravitational time dilation. The amount of redshift directly measures how much time has slowed down in these regions. These ion line observations reveal not just time dilation, but its detailed variation with distance from the black hole. Material orbiting at different radii experiences different degrees of time dilation, creating a characteristic profile in the observed spectrum. By analyzing these line shapes, astronomers can map the spacetime geometry around black holes and test Einstein's predictions in the strongest gravitational fields known to exist. The Event Horizon Telescope's historic images of black holes in galaxies, M87, and our own Milky Way provide visual evidence of extreme time dilation effects. The bright ring visible in these images represents photons orbiting in the photon sphere just outside the event horizon, where time dilation approaches its maximum possible value. The existence and properties of this ring confirm theoretical predictions about how extreme gravity affects both matter and light. But perhaps the most spectacular observable effect occurs when entire stars venture too close to supermassive black holes, events called tidal disruption events. As a star approaches within a few times the black hole's Schwarzschild radius, the differential gravitational forces begin tearing it apart. The time dilation effects become so severe that astronomers observe the disruption process playing out in slow motion from our distant perspective. The Zwicky Transient Facility has detected dozens of these stellar destruction events, revealing how time dilation affects the observed light curves. The brightening and fading of the disrupted stellar material occurs much more slowly than would be expected without time dilation effects. The observations match computer simulations that include general relativistic time dilation, providing direct evidence that these effects operate in real astrophysical environments. Individual stars orbiting supermassive black holes provide another powerful laboratory for observing time dilation. The star S2, which orbits the supermassive black hole at our galaxy's center, completed its closest approach in 2018, reaching just 120 times the black hole's event horizon radius. During this closest approach, time dilation effects became clearly detectable. The gravity instrument at the Very Large Telescope Interferometer measured S2's orbital motion with unprecedented precision during this close passage. The observations revealed both gravitational redshift and time dilation effects exactly as Einstein's theory predicted. S2's light appeared redshifted during closest approach, and the star's orbital period showed the modifications expected from general relativistic effects. These observations of S2 represent the most precise test of general relativity in strong gravitational fields ever achieved. The measurements confirm Einstein's predictions to better than 0.1% accuracy, demonstrating that time dilation operates exactly as theoretical calculations suggest, even in the extreme environment near a supermassive black hole. Gravitational wave detections by LIGO and Virgo observatories have opened an entirely new window for studying time dilation effects near black holes. When black holes merge, the final moments of their spiral approach involve extreme time dilation as they orbit at significant fractions of the speed of light within each other's strong gravitational fields. The gravitational wave signals carry encoded information about these time dilation effects. The frequency evolution of gravitational waves during black hole mergers shows characteristic patterns that depend on the time dilation experienced by the orbiting black holes. As the orbit tightens and gravitational fields strengthen, the rate of frequency change itself becomes affected by time dilation. LIGO's detections have confirmed these patterns match general relativity's predictions with remarkable precision. Future gravitational wave observations may detect even more extreme time dilation effects. Third-generation detectors like Einstein Telescope and Cosmic Explorer will be sensitive enough to observe black hole mergers from much greater distances. potentially detecting systems where time dilation reaches even more extreme values. These observations could test general relativity in previously inaccessible regimes. The observable effects of time dilation extend beyond individual black holes to influence the large-scale structure of our universe. Supermassive black holes at the centers of galaxies affect the evolution of their host systems through time dilation effects on infalling matter. Material falling toward these central monsters experiences severe time dilation that affects star formation rates, gas cooling processes, and galactic evolution timescales. Computer simulations of galaxy formation that include general relativistic effects show how time dilation near central black holes influences the growth and evolution of massive galaxies. The time dilation experienced by gas falling toward the central black hole affects feedback processes that regulate star formation throughout the galaxy, demonstrating how these extreme physics effects influence cosmic structure on the largest scales. Observations of quasars, extremely luminous objects powered by material falling into supermassive black holes, reveal time dilation effects and their light output variations. The flickering and changes in brightness from these distant objects show characteristic timescales that reflect the time dilation experienced by matter in the strong gravitational fields near the central black holes. The upcoming James Webb Space Telescope will provide unprecedented capabilities for detecting time dilation effects around black holes. Its infrared sensitivity will enable observations of stars orbiting much closer to the galactic center black hole than previously possible, potentially detecting time dilation effects from objects venturing within just a few event horizon radii. Next-generation ground-based telescopes, like the extremely large telescope, will have the resolution to study individual stars orbiting black holes in nearby galaxies, extending these precise tests of time dilation to supermassive black holes with different masses and properties. These observations will test whether time dilation effects operate universally across the full range of black hole masses. The observable effects of time dilation near black holes have also enabled tests of alternative theories of gravity. Some proposed modifications to general relativity predict slightly different time dilation effects, and the precision of current observations is beginning to constrain these alternative theories. Future observations may definitively rule out modifications that don't match the observed time dilation patterns. Laboratory experiments continue to verify the same physics that governs time dilation near black holes. Atomic clock experiments have now achieved precision sufficient to detect time dilation effects from height differences of less than 1 meter on Earth's surface. These laboratory tests confirm that the same fundamental physics operates across all scales, from tabletop experiments to the most extreme environments near black holes. The study of observable time dilation effects near black holes represents one of the great triumphs of modern astronomy and physics. These observations have transformed Einstein's mathematical insights into verified reality, demonstrating that the universe operates according to principles that challenge human intuition, but reveal profound truths about the nature of space and time. As observational capabilities continue advancing, these cosmic laboratories will provide even more stringent tests of our understanding of reality's fundamental structure. Chapter 8. Time's Journey. The story of time dilation near black holes represents more than just exotic physics. It reveals the profound journey that human understanding has taken from Newton's absolute time to Einstein's relative time to the quantum mysteries that continue to challenge our comprehension today. This intellectual odyssey has fundamentally transformed how we perceive reality itself and our place within the cosmic order. Newton's universe operated like a perfect clockwork mechanism where time flowed uniformly throughout all of creation. In this framework, simultaneity had absolute meaning. Events that occurred now happened at the same moment everywhere in the universe. This intuitive understanding matched human experience and seemed obviously correct for nearly 3 centuries. Time was the stage upon which physical processes unfolded, separate from and unaffected by the matter and motion it contained. The first cracks in this absolute framework appeared in the late 19th century with the mysterious properties of electromagnetic radiation. James Clerk Maxwell's equations revealed that light traveled at a constant speed regardless of the motion of its source, a result that seemed incompatible with Newton's absolute space and time. The Michelson-Morley experiment's failure to detect Earth's motion through the proposed light-carrying medium forced physicists to confront the possibility that their fundamental assumptions about space and time might be wrong. Einstein's special relativity in 1905 shattered the Newtonian framework by revealing that time itself was relative to motion. The counterintuitive prediction that moving clocks run slow seemed absurd to many physicists, but experimental verification began almost immediately. Observations of cosmic ray muons reaching Earth's surface despite their short lifetimes provided early evidence that time dilation was real, not merely theoretical speculation. The conceptual leap to general relativity a decade later extended time's relativity from motion to gravity itself. Einstein's insight that gravity and acceleration were fundamentally equivalent led to the revolutionary prediction that massive objects curve spacetime and thereby affect the flow of time. This wasn't just a refinement of existing physics. It was a complete reconceptualization of the relationship between matter, space, and time. Early tests of general relativity focused on relatively weak gravitational fields, where time dilation effects remained small but measurable. Arthur Eddington's 1919 solar eclipse expedition confirmed Einstein's prediction about light bending near the sun, while the Pound-Rebka experiment 40 years later demonstrated gravitational redshift in Earth's gravitational field. These measurements established that time dilation was real, but seemed far removed from everyday experience. The discovery of neutron stars in 1967 provided the first astrophysical laboratories where extreme time dilation effects became significant. These incredibly dense stellar remnants, packing more mass than the Sun into spheres barely 20 kilometers across, created gravitational fields strong enough to produce measurable time dilation. Radio observations of pulsars rapidly rotating neutron stars revealed timing effects consistent with Einstein's predictions for strong field gravity. But it was the theoretical prediction and eventual discovery of black holes that truly brought extreme time dilation into focus. John Wheeler's coining of the term black hole in 1967 helped popularize the concept, but it took decades of theoretical development to fully understand the implications of infinite time dilation at event horizons. The mathematical machinery required to describe such extreme effects pushed the boundaries of theoretical physics. The 1970s brought revolutionary insights about black hole physics through the work of Stephen Hawking, Jacob Bekenstein, and others who revealed deep connections between black holes, thermodynamics, and information theory. Their discoveries showed that black holes weren't just exotic gravitational objects, they were laboratories where general relativity encountered quantum mechanics in the most extreme possible conditions. Technological advances in the late 20th century finally enabled direct observations of time dilation effects near black holes. X-ray telescopes launched into space could detect the characteristic signatures of matter spiraling into black holes, revealing gravitational redshift and time dilation in real astrophysical systems. These observations transformed time dilation from a theoretical prediction into an observed phenomenon. The development of atomic clocks with extraordinary precision opened new frontiers for testing time dilation effects. By the 1970s, atomic clocks could detect time dilation from airplane flights and Earth's rotation. Today's optical atomic clocks can measure time dilation effects from height changes of just centimeters, bringing laboratory precision to tests of Einstein's most exotic predictions. GPS satellites provided an unexpected practical application of time dilation physics. The system's reliance on precise timing forced engineers to account for both special and general relativistic effects, making GPS the first technology that required Einstein's insights for routine operation. Every navigation calculation performed by smartphones demonstrates that time dilation isn't just academic theory. It's essential for modern life. The 21st century has witnessed an explosion of observations confirming extreme time dilation effects near black holes. Space telescopes have detected iron emission lines from gas orbiting just outside event horizons. Gravitational wave observatories have measured the dynamics of black hole mergers. And the Event Horizon Telescope has imaged the shadows cast by black holes themselves. Each observation confirms Einstein's century-old predictions with increasing precision. But these observations have also revealed new mysteries. The information paradox, the question of what happens to information that falls into black holes, connects time dilation to fundamental questions about quantum mechanics and the nature of reality itself. Theoretical physicists continue debating whether information is destroyed, preserved, or somehow encoded on black hole surfaces through holographic principles. Recent theoretical work has revealed potential connections between time dilation near black holes and some of the deepest problems in physics. The AD-CFT correspondence suggests that gravity in curved spacetime might be equivalent to quantum field theories on the boundaries of that spacetime. If correct, this would mean that time dilation effects near black holes are fundamentally quantum mechanical phenomena. The quest to understand quantum gravity, a theory that would unify general relativity with quantum mechanics, may ultimately require new insights about the nature of time itself. Some theories suggest that time might be emergent rather than fundamental, arising from more basic quantum processes. If true, the extreme time dilation near black holes might provide clues about time's deepest nature. Future observations promise to push tests of time dilation into even more extreme regimes. Next-generation gravitational wave detectors may observe black hole mergers from the universe's earliest epochs, providing data about time dilation in environments that no longer exist today. Space-based gravitational wave observatories could detect mergers of supermassive black holes where time dilation effects reach unprecedented extremes. The philosophical implications of time dilation near black holes continue to challenge human understanding. If time can slow down, speed up, or even potentially flow backward near rotating black holes, what does this mean for concepts like causality, free will, and the arrow of time? These questions push beyond physics into fundamental issues about the nature of existence and consciousness. Educational challenges arise from teaching physics that contradicts everyday intuition. Students must learn to accept that their direct experience of uniform time flow is limited and provincial valid, only in weak gravitational fields and at low speeds. The universal truth is far stranger. Time is personal, relative, and fundamentally connected to the distribution of matter and energy throughout the cosmos. The journey from Newton's absolute time to Einstein's relative time to the quantum mysteries surrounding black holes represents one of the greatest intellectual adventures in human history. Each step has revealed that reality is far more subtle and surprising than our intuitions suggest. Time dilation near black holes stands as perhaps the most extreme manifestation of this strange universe we inhabit. As our understanding continues evolving, time dilation near black holes serves as both a testing ground for our most advanced theories and a reminder of how much we still don't understand. The journey of human comprehension continues, driven by the same curiosity that led Einstein to imagine riding alongside light beams and wonder what the universe would look like from that impossible perspective. Chapter 9. Cosmic Perspective. When you step back and contemplate the universe as revealed through time dilation near black holes, A profound shift in perspective emerges that challenges the very foundations of human experience and reveals our cosmos as a place far stranger and more beautiful than everyday intuition suggests. The discovery that time itself is malleable, stretchable, and fundamentally personal transforms not just our understanding of physics, but our comprehension of existence itself. Consider what time dilation near black holes reveals about the nature of reality. The universe operates according to principles that transcend human perception and experience. Your direct sensation of time flowing uniformly is not a fundamental truth about reality. It's a local phenomenon that applies only within the relatively weak gravitational environment of Earth's surface. The universal truth is far more profound. Time is relative, personal, and intimately connected to the geometry of spacetime itself. This realization places human experience in cosmic context. We evolved in a gravitational environment where time dilation effects remain negligible in daily life. Our biological clocks, our psychological perception of duration, our entire cognitive framework for understanding temporal relationships developed in conditions where Einstein's most exotic predictions remain hidden beneath the threshold of perception. We are, in a very real sense, beings adapted to a narrow slice of reality's full spectrum. Yet through scientific investigation, humans have transcended these evolutionary limitations to discover truths about time that no biological evolution could have prepared us to understand intuitively. The mathematics of general relativity has given us conceptual tools to comprehend regions of the universe where our direct experience would be not just inadequate but actively misleading. This represents one of the greatest triumphs of human intellect over the limitations of human perception. The cosmic perspective revealed by time dilation extends far beyond black holes themselves. Every massive object in the universe creates its own local temporal environment. Planets, stars, galaxies, and clusters of galaxies all warp spacetime and thereby influence the flow of time in their vicinity. The universe is not a stage with uniform time flow. It's a vast symphony of different temporal rhythms, each determined by the local distribution of matter and energy. Our solar system exists within the gravitational influence of the Milky Way's supermassive central black hole, which contains over 4 million times the mass of our Sun. Though we orbit roughly 26,000 light-years from this monster, its gravitational influence subtly affects time flow throughout our galaxy. We are living within the temporal environment created by one of the most massive objects in the local universe, experiencing a cosmic rhythm set by extreme physics we're only beginning to understand. The implications extend to life itself. If life exists elsewhere in the universe, particularly near more massive objects or in stronger gravitational fields, those beings would experience time differently than we do. A civilization orbiting close to a supermassive black hole might experience centuries passing while only years elapse on Earth. Their thoughts, their biological processes, their entire experience of existence would unfold in a different temporal framework than our own. This possibility raises profound questions about communication and contact with extraterrestrial civilizations. If we receive signals from beings living in strong gravitational fields, the time dilation effects might mean that their real-time communication represents ancient history from our perspective, or vice versa. The universal speed limit imposed by light, combined with gravitational time dilation, creates temporal barriers to cosmic communication that go far beyond simple distance. The long-term fate of our universe becomes even more profound when viewed through the lens of time dilation. As cosmic expansion continues and matter becomes increasingly concentrated into black holes, vast regions of space will experience dramatically different temporal flows. The universe's far future might consist of isolated islands of matter experiencing radically different temporal rhythms as they slowly evaporate through Hawking radiation. From the perspective of matter falling into black holes during this far future epoch, the external universe would appear to age and evolve at tremendous speeds due to time dilation effects. These hypothetical observers would witness the entire remaining history of the cosmos compressed into brief moments of their personal time. In a very real sense, different regions of the universe would experience different versions of cosmic history. But perhaps most profound is what time dilation near black holes reveals about the nature of existence itself. The fact that time can slow down, speed up, or near event horizons appear to stop completely suggests that our normal concepts of past, present, and future are far more limited than we imagine. The universe operates according to principles where simultaneity becomes ill-defined, and the temporal relationships between events depend fundamentally on where and how you observe them. This challenges basic assumptions about consciousness and experience. If time is relative and personal, what does this mean for concepts like memory, anticipation, and the continuity of consciousness? Philosophers and physicists continue debating whether consciousness itself might be affected by extreme time dilation or whether subjective experience remains unchanged regardless of the local temporal environment. The cosmic perspective also reveals deep connections between seemingly unrelated phenomena. The same physics that governs time dilation near black holes explains why GPS satellites require relativistic corrections, why atomic clocks run differently at different altitudes, and why the universe appears to have a cosmic microwave background with nearly uniform temperature. General relativity provides a unified framework that connects the smallest laboratory experiments to the most extreme cosmic environments. Understanding time dilation near black holes also illuminates the role of information in our universe. If information falling into black holes becomes stretched and redshifted to the point where it appears frozen at event horizons from external perspectives, this suggests deep connections between information theory, thermodynamics, and the fundamental structure of spacetime. The universe might be, in some sense, an information processing system where black holes play crucial roles in information storage and processing. The aesthetic beauty of these discoveries cannot be ignored. Einstein's equations, which describe how matter curves spacetime and thereby affects time flow, represent mathematics of extraordinary elegance. The fact that such beautiful mathematical structures describe the deepest aspects of physical reality suggests profound connections between mathematical truth and physical existence that philosophers have contemplated for millennia. Yet this beauty comes with humbling implications. If our most advanced theories about black holes and time dilation are correct, then the universe operates according to principles that transcend not just human intuition, but potentially human comprehension itself. We may be approaching fundamental limits to what beings with our cognitive architecture can understand about the deepest aspects of reality. The technological implications of understanding time dilation extend beyond current applications like GPS. Future space exploration might deliberately exploit time dilation effects for interstellar travel, allowing astronauts to journey to distant stars while experiencing minimal aging relative to Earth-bound observers. The physics that creates extreme time dilation near black holes might ultimately enable humanity to transcend the normal limitations of biological lifespans. But perhaps the most important cosmic perspective revealed by time dilation near black holes concerns our place in the universe. We exist as conscious observers in a cosmos where time itself is relative and malleable. Our ability to understand these exotic effects despite our evolution in mundane gravitational environments suggests something remarkable about consciousness and intelligence as cosmic phenomena. You are not separate from the universe that exhibits these exotic time dilation effects. You are part of it. Your consciousness evolved within a cosmos where time flows differently near massive objects, where black holes stretch seconds into eternities, and where the fundamental nature of temporal experience depends on your location in the gravitational landscape of spacetime. You are a manifestation of the universe, developing the capacity to understand its own temporal structure. The journey to understand time dilation near black holes represents more than scientific discovery. It represents the universe awakening to its own nature through conscious observation. When you contemplate how gravity slows time near black holes, you participate in the cosmos, examining its own deepest principles. This perspective transforms scientific understanding from mere academic knowledge into a profound meditation on existence itself. Chapter 10. Ultimate Reality at the Deepest Level. Time dilation near black holes reveals that reality itself operates according to principles so far removed from human intuition that they challenge the very categories through which we organize experience and understanding. The discovery that time is not absolute but relative, not universal but personal, not constant but malleable, opens doorways to questions about the ultimate nature of existence that extend far beyond physics into the realms of philosophy, consciousness, and meaning itself. The mathematics describing time dilation near black holes, Einstein's field. Equations represent more than just successful physics. They describe the fundamental geometry of existence itself, the way that matter and energy determine the very shape of the stage upon which all physical processes unfold. When massive objects curve spacetime severely enough to create black holes, they aren't just affecting local physics, they're reshaping the basic structure of reality in their vicinity. This geometric view of existence suggests that what we call physical laws might be better understood as descriptions of how reality's fundamental structure manifests under different conditions. Time dilation near black holes isn't something that happens within spacetime. It's an expression of how spacetime itself can be organized. The extreme temporal effects represent reality exploring its own geometric possibilities in the most extreme environments. The fact that time can slow down near black holes, approach standstill at event horizons, and flow differently throughout the universe implies that temporal experience is far more fundamental to reality's structure than previously imagined. If time is geometric rather than absolute, then consciousness, which experiences itself as temporally extended, might be more intimately connected to the basic architecture of existence than we ever suspected. Consider what this means for the nature of causality itself. In regions of extreme time dilation, the usual temporal relationships between cause and effect become severely distorted. Events that appear simultaneous to distant observers occur at different times for local observers, while events separated by eons in coordinate time might appear nearly simultaneous to someone falling toward a black hole's event horizon. This suggests that causality might be more flexible and observer-dependent than our everyday experience indicates. The information paradox surrounding black holes pushes these questions about ultimate reality even deeper. If information falling past event horizons cannot escape, but also cannot be destroyed as quantum mechanics demands, then black holes might represent regions where the usual relationship between information and spacetime breaks down completely. Some theoretical physicists speculate that black hole interiors might not exist as independent regions of spacetime, but rather as holographic projections of information encoded on event horizon surfaces. This holographic principle, if correct, would imply that reality's apparent three-dimensional structure might be emergent rather than fundamental. The information describing any region of spacetime might be encoded on the boundary of that region, suggesting that spatial extension itself could be a kind of illusion arising from more fundamental information processing dynamics. Black holes, in this view, become cosmic computers processing information in ways that transcend our normal understanding of computation and storage. But the ultimate implications extend beyond information theory to questions about consciousness and observation. Quantum mechanics already suggests that observation plays a fundamental role in determining physical reality's structure. If time dilation near black holes represents reality's most extreme manifestation of observer-dependent physics, then consciousness might be more central to the universe's operation than materialist philosophies have traditionally assumed. The fact that different observers experience radically different temporal realities near black holes, with some seeing events frozen at event horizons while others experience normal time flow, suggests that there might be no single, objective description of reality that encompasses all possible perspectives. Instead, reality might consist of multiple, equally valid descriptions that depend fundamentally on the observer's location and motion within spacetime. This observer-dependent nature of reality near black holes connects to ancient philosophical questions about the relationship between appearance and reality, perception and existence, consciousness and cosmos. If time itself depends on the observer's reference frame, then the temporal categories through which consciousness organizes experience might be more fundamental to reality's structure than previously imagined. The extreme time dilation near black holes also illuminates questions about the arrow of time, why time appears to flow from past to future rather than the reverse. In regions where time dilation becomes extreme, the usual temporal ordering of events breaks down, and different observers might disagree about which events are earlier or later. This suggests that time's apparent directionality might emerge from thermodynamic processes rather than representing a fundamental aspect of spacetime geometry. Yet despite these profound challenges to conventional understanding, time dilation near black holes reveals deep mathematical harmonies that suggest reality operates according to principles of extraordinary beauty and elegance. Einstein's field equations, which describe how matter curves spacetime, represent mathematics of remarkable sophistication that nevertheless yields predictions matching observations with extraordinary precision. This mathematical beauty suggests aesthetic principles might be fundamental to reality's deepest structure. The convergence of general relativity and quantum mechanics near black holes, where both theories become essential for understanding physical processes, points toward an even deeper theory that might unify these frameworks into a single description of reality's ultimate nature. String theory, loop quantum gravity, and other approaches to quantum gravity represent humanity's attempts to glimpse this deeper unity, but the final theory remains elusive. Some physicists speculate that time itself might be emergent rather than fundamental, arising from more basic quantum processes that don't involve temporal concepts at all. If correct, the extreme time dilation near black holes might provide clues about time's deeper origin and the quantum processes from which temporal experience emerges. Understanding black holes might ultimately require transcending the temporal categories through which we normally understand physics. The anthropic implications of time dilation near black holes raise questions about the relationship between consciousness and cosmic structure. If the universe's fundamental constants were slightly different, black holes might not exist, or their properties might be dramatically altered. The fact that we exist in a universe where such extreme time dilation effects are possible suggests either remarkable cosmic fine-tuning or the existence of multiple universes with different physical properties. But perhaps the most profound insight revealed by time dilation near black holes concerns the nature of existence itself. The discovery that reality operates according to principles so foreign to human intuition suggests that existence transcends the categories through which finite minds attempt to comprehend infinite phenomena. We are part of a universe whose deepest operations exceed our conceptual frameworks while remaining accessible to mathematical investigation. This creates a paradox worthy of contemplation. Consciousness, evolved in mundane gravitational environments, has developed the capacity to understand physics that transcends its experiential boundaries. Through mathematics, human minds can grasp truths about time and space near black holes that no biological evolution could have prepared us to comprehend directly. This suggests something remarkable about the relationship between consciousness and cosmos, that mind and universe might be more intimately connected than materialist philosophies traditionally assume. The ultimate reality revealed by time dilation near black holes is that existence itself is far stranger, more beautiful, and more mysterious than everyday experience suggests. Time is not the rigid backdrop against which events unfold. It's a dynamic aspect of realities, geometry that responds to matter and energy in ways that create temporal landscapes of extraordinary diversity. Near black holes, these landscapes become so exotic that familiar concepts of duration, simultaneity, and temporal sequence break down completely. As you contemplate these insights, remember that you are not separate from the universe that exhibits these exotic properties. Your consciousness represents the cosmos, developing the capacity to understand its own temporal structure. When you grasp how gravity slows time near black holes, you participate in reality's self-examination through conscious observation and mathematical investigation. The journey to understand time dilation near black holes ultimately reveals that reality transcends all finite attempts at comprehension while remaining mysteriously accessible to mathematical exploration. This accessibility suggests deep connections between mind and cosmos, consciousness and spacetime, observation and existence that point toward truths about ultimate reality that continue to exceed our grasp while drawing us deeper into wonder and investigation. The exploration of time dilation near black holes ultimately confronts us with the most fundamental question about existence. What is the nature of reality itself when our most basic assumptions about time and space prove to be illusions created by our limited perspective? The answer, emerging from decades of theoretical development and observational confirmation, suggests that reality operates according to principles so profound they challenge not just scientific understanding, but the very categories through which consciousness organizes experience. Recent developments in quantum gravity research have revealed that time dilation near black holes might connect to the deepest puzzles about information and computation in our universe. The holographic principle suggests that all the information contained within any volume of space can be encoded on the boundary of that volume. Near black holes, this principle reaches its most extreme expression. The entire three-dimensional interior of a black hole might be equivalent to information encoded on its two-dimensional event horizon surface. This holographic relationship implies that spatial extension itself might be emergent rather than fundamental. What we experience as three-dimensional reality could arise from information processing dynamics operating on lower dimensional surfaces. Black holes become cosmic computers of unimaginable power, processing information through mechanisms that transcend our current understanding of computation, storage, and retrieval. The time dilation effects we observe might represent the visible manifestation of computational processes operating at reality's deepest level. The connection between computation and consciousness raises even more profound questions. If reality emerges from information processing and consciousness involves information integration, then the extreme information processing environments near black holes might represent laboratories where consciousness and cosmos intersect in ways we're only beginning to glimpse. Some theoretical physicists speculate that consciousness itself might be a fundamental feature of information processing systems, suggesting that black holes could be conscious entities operating according to principles that transcend biological intelligence. These speculations connect to ancient philosophical traditions that view consciousness as fundamental to reality's structure rather than an emergent property of complex matter. The time dilation effects near black holes, which depend fundamentally on the observer's reference frame, suggest that observation and consciousness might play more central roles in determining reality's structure than materialist philosophies have traditionally acknowledged. The mathematical beauty of Einstein's equations describing time dilation near black holes points toward aesthetic principles that might be fundamental to existence itself. The fact that such elegant mathematical structures describe the most extreme physical phenomena suggests deep connections between mathematical truth and physical reality that philosophers have contemplated for millennia. Beauty, in this view, becomes not just a human aesthetic preference, but a fundamental organizing principle of cosmic architecture. Yet this mathematical elegance comes with humbling implications. The equations that successfully predict time dilation effects near black holes operate according to logical structures that transcend human intuition while remaining accessible to mathematical investigation. This suggests that reality's deepest operations might always exceed direct human comprehension while remaining mysteriously open to rational analysis through mathematical abstraction. The theological implications of time dilation near black holes deserve contemplation. If time itself is relative and observer-dependent, what does this mean for concepts of eternity, divine presence, and ultimate meaning? Traditional religious frameworks often assume absolute temporal categories, but the physics of black holes reveals a universe where temporal relationships depend fundamentally on spatial location and gravitational environment. This might require theological thinking to evolve beyond classical concepts of divine temporality. Some philosophers of religion have suggested that the extreme time dilation near black holes provides metaphors for understanding divine eternity regions where time approaches standstill might represent something analogous to eternal presence. Others argue that the observer-dependent nature of time dilation reveals the inherently relational character of existence, supporting theological frameworks that emphasize relationship over substance as reality's fundamental structure. The practical implications of understanding time dilation extend far beyond current technological applications. Future civilizations might deliberately exploit these effects for preservation and longevity, using controlled approaches to black holes as cosmic time machines that allow biological beings to journey far into the future while experiencing minimal aging. The physics that creates extreme time dilation might ultimately enable intelligence to transcend the normal limitations imposed by finite lifespans. But such applications would require technological capabilities that seem almost miraculous from our current perspective. Safely approaching the regions where extreme time dilation occurs would demand mastery over gravitational fields, exotic matter with negative energy densities, and navigation systems capable of operating in severely curved spacetime. These technologies might be achievable for civilizations far more advanced than our own, opening possibilities for cosmic engineering projects that exploit spacetime geometry itself. The search for extraterrestrial intelligence takes on new dimensions when considered through the lens of time dilation near black holes. Advanced civilizations might deliberately establish themselves in regions of extreme time dilation, allowing them to observe the long-term evolution of the universe while experiencing relatively brief subjective time. From our perspective, such civilizations might appear to operate on geological or cosmic timescales, making communication across temporal barriers as challenging as communication across spatial distances. The ultimate fate of consciousness in a universe dominated by black holes becomes a question of profound significance. As cosmic expansion continues and matter becomes increasingly concentrated into black holes, conscious observers might face choices about whether to preserve themselves through technological means or accept a natural progression toward cosmic heat death. The time dilation effects near black holes offer potential escape routes from this cosmic predicament, but exploiting them would require wisdom and technological capability that transcend current human limitations. The deepest mystery revealed by time dilation near black holes might be the nature of existence itself. The fact that reality operates according to principles so foreign to human intuition suggests that existence transcends all finite attempts at comprehension, while remaining mysteriously accessible to mathematical investigation. This accessibility points toward connections between mind and cosmos that challenge purely materialist explanations of consciousness and intelligence. Perhaps consciousness represents the universe's method for understanding its own structure through mathematical investigation and observational science. If correct, then the study of time dilation near black holes represents more than scientific discovery. It represents reality examining its own deepest principles through conscious observation and rational analysis. You participate in this cosmic self-examination every time you contemplate how gravity affects the flow of time. The ultimate reality revealed by time dilation near black holes is that existence itself operates according to principles of extraordinary beauty, mystery, and transcendence that exceed human comprehension, while drawing conscious observers ever deeper into wonder and investigation. Time is not separate from space. Matter is not separate from geometry. And consciousness might not be separate from the cosmic processes through which the universe comes to understand its own nature. Throughout this journey into the extreme physics near black holes, we've discovered that time itself is not what it seems. We began with Einstein's revolutionary insight that time flows differently for different observers, explored how massive objects curve the very fabric of spacetime, and traveled to the ultimate boundary where time appears to stop completely. We've seen how falling clocks reveal the personal nature of temporal experience, how gravitational redshift carries the signature of time dilation across cosmic distances, and how the event horizon represents the mathematical limit where our normal understanding of time breaks down entirely. But perhaps the most profound insight we've uncovered is that time dilation near black holes reveals the universe as a place of extraordinary beauty and mystery that transcends human intuition while remaining accessible to human understanding. The mathematics that Einstein developed over a century ago continues to predict observations with stunning accuracy, from the subtle corrections required for GPS satellites to the dramatic redshift patterns observed in matter spiraling into cosmic monsters millions of times more massive than our Sun. As you contemplate these discoveries, consider how they transform your understanding of existence itself. Every massive object in the universe, from planets to stars to the supermassive black holes at galactic centers, creates its own temporal environment where time flows according to local gravitational conditions. You are living within a cosmic symphony of different temporal rhythms, with black holes creating the most extreme tempo variations in this grand cosmic orchestra. The observable effects we've explored represent more than just exotic physics. They provide direct evidence that reality operates according to principles that challenge every assumption about the nature of space and time. When astronomers detect iron emission lines redshifted by extreme gravity, when gravitational wave detectors measure the final moments of black hole mergers, when the Event Horizon Telescope images the shadows cast by event horizons themselves, they're not just observing distant astrophysical phenomena, they're witnessing the fundamental nature of reality itself. These observations have confirmed Einstein's most counterintuitive predictions with extraordinary precision while revealing new mysteries that continue to challenge our understanding. The information paradox, the possibility of quantum firewalls, the potential holographic nature of reality, these concepts push the boundaries of human comprehension while pointing toward even deeper truths about the ultimate structure of existence. But the journey to understand time dilation near black holes also reveals something remarkable about consciousness itself. Through mathematics and careful observation, human minds have transcended the limitations of direct experience to comprehend physics that operates in the most extreme environments imaginable. This represents one of the greatest achievements of human intelligence, the ability to understand truths about reality that no biological evolution could have prepared us to grasp intuitively. When you experience time flowing uniformly through your daily life, remember that this experience represents just one narrow slice of temporal reality. Near black holes, time can slow to a crawl, approach complete standstill, or flow at rates that differ from distant observers by factors of thousands or millions. Your personal experience of time, though real and valid, is deeply provincial compared to the full spectrum of temporal possibilities that exist throughout the universe. Yet, you are not separate from this strange universe where time behaves so exotically. You are part of it. Your atoms were forged in stellar cores. Your planet orbits within the gravitational influence of our galaxy's central supermassive black hole. And your consciousness represents the universe developing the capacity to understand its own temporal structure. When you contemplate how gravity slows time near black holes, you participate in reality's self-examination through conscious observation. The cosmic perspective revealed by these discoveries places human existence in profound context. We evolved in gravitational environments where time dilation effects remain hidden beneath the threshold of everyday perception. Yet through scientific investigation, we've uncovered truths about time that challenge the very foundations of experience. This suggests something remarkable about the role of consciousness in cosmic evolution, that the universe might be inherently designed for self-understanding through intelligent observation. As our observational capabilities continue advancing, the study of time dilation near black holes will provide even more stringent tests of our understanding about reality's fundamental nature. Future gravitational wave detectors may observe black hole mergers from the universe's earliest epochs. Next-generation telescopes will study individual stars orbiting closer to supermassive black holes than ever before. And space-based observatories might detect exotic physics that transcends our current theoretical frameworks. But beyond the technological achievements and scientific discoveries, the study of time dilation near black holes represents something deeper: humanity's ongoing quest to understand the ultimate nature of existence itself. Each new observation, each theoretical breakthrough, each deeper understanding of how gravity affects time brings us closer to grasping truths about reality that exceed our current comprehension, while drawing us ever deeper into wonder and investigation. The mathematics describing time dilation near black holes will continue revealing new insights about the relationship between matter, energy, space, and time. The geometric view of gravity as space-time curvature connects to quantum mechanics in ways that might ultimately yield a complete theory of reality's fundamental structure. String theory, loop quantum gravity, and other approaches to understanding quantum spacetime represent humanity's attempt to glimpse the deeper unity that underlies all physical phenomena. If you found this exploration of time dilation near black holes fascinating, subscribe and give this video a thumbs up. The universe is full of phenomena that challenge our understanding and reveal the extraordinary beauty of reality's deepest structure. Check out my video on quantum mechanics and consciousness. I think you'll find it equally mind-expanding as we continue exploring the mysteries of existence. As you go about your daily life after watching this, remember that you're living within curved space-time, created by massive objects throughout the cosmos. When you check the time on your phone, remember that GPS satellites must account for Einstein's predictions about time dilation. When you look up at the night sky, remember that you're seeing light that has traveled through regions where time flows differently than it does here on Earth. The black holes scattered throughout our galaxy and beyond continue their cosmic dance, creating regions where time slows to a crawl and eventually appears to stop completely. Matter falling into these cosmic monsters experiences the universe's most extreme manifestations of time dilation while revealing truths about reality that push human understanding to its limits and beyond. You are part of a universe where such extraordinary physics operates, a cosmos far stranger and more beautiful than everyday experience suggests. When you contemplate how gravity slows down time near black holes, you're not just learning about exotic physics. You're participating in the universe's ongoing project of self-understanding through conscious observation and mathematical investigation. This represents one of the most profound activities available to conscious beings, using the capacity for rational thought to glimpse truths about existence that transcend the limitations of direct experience, while pointing toward even deeper mysteries that continue to exceed our grasp. Time flows differently throughout the cosmos and near black holes. It reveals its most exotic and mysterious nature, a cosmic reminder that reality itself is far more strange, beautiful, and profound than our everyday experience can possibly suggest.